Welcome everyone. In this video we are going to prove the work-energy theorem. That is, the net work done on an object is equal to the change in kinetic energy of that object. We want to prove this, which is called the work-energy theorem. Now I'm going to make the proof where A, the acceleration, is a constant. So I will use uniformly accelerated motion, UAM motion ideas. Now you don't need to do this, and in a future video if you want I can do the general proof with calculus. It isn't very different, but now we're sticking to kinematics, equations and UAM. So let's get started. Now we need to first have a drawing. Okay, let's draw it. Let's draw it. So we have an object of mass m and we're applying a force. And this isn't the force that we're applying actually. This is the net force. Okay, perhaps you are pushing to the right with a force F and there is friction to the left. When you subtract these two, what is left is F net, the net force. Okay, and of course the vertical direction cancel out anyways. So we have this, and the object is going to go to the right as well. The delta x is also going to be to the right. So you can see that F net and delta x are in the same direction. This is another assumption that we are making to just make the calculations simpler, basically. All right? So what is the work in this case? Well, work is going to be F net, and I am dropping the vector because it is the magnitude of the force. Work is a scalar, that is very important. So F net times delta x, we would say cosine of 0 because the angle between is 0, but that is just 1, right? Cosine of 0 is 1, so we don't even need to write it. So we have this for work, and we can even call this the net work, because it is the work done by the net force. Cool? Now, this is equal to, we see F net, and that should remind you of two letters, M and A. That is Newton's second law. Force, the net force equals mass times acceleration. So let's write that. We have MA. And by the way, in a previous video, I proved that the net force is equal to mass times acceleration. You can find that proof from the cards right now, also from the descriptions part. Now we also have delta x. Cool? Here I'm going to now use a kinematics equation. That equation is, let me write it, v final squared is equal to v naught squared, the initial velocity squared, plus 2a delta x. And this is the final velocity. And I also proved this in a previous video. You can find it from the cards right now, also from the descriptions part. Now, with that being said, I want to focus on this part, a times delta x, because that part appears here. I want to substitute for it. Why not? Let's do it. What could happen, right? So, let me solve for a times delta x then. We are solving the orange equation. So we have a times delta x is equal to, we subtract v naught squared from both sides. So we have v final squared minus v naught squared. We need to divide by 2. So we do that. Now I'm just going to take this guy and substitute it here. All right, let's do that. So then this is equal to, we have the mass, and then instead of a times delta x, I am writing v final squared minus v naught squared divided by 2. And then with the parentheses. Now I can distribute the multiplication. I can get rid of the parentheses so that I am left with 1 over 2m v final squared minus 1 over 2m v naught squared. And you might say, aha, I see where this is going. Because what is the definition of kinetic energy? Let's write it here, perhaps. Let's write it here. So kinetic energy, that's not looking good. Kinetic energy is defined to be 1 over 2 mv squared. And we have something that is very close to it. We have final and initial though, so it is simply kinetic energy final minus kinetic energy initial. And that is of course going to give you delta K, the change in the kinetic energy, because the final minus initial always gives the delta. And that is it. We proved that the net work done on an object is equal to the change in kinetic energy of that object. Now I want to make an interesting remark here. You might be surprised that, we encountered kinetic energy here. How could that come to be? Well, in fact, we didn't encounter it. The scientists at some point did this calculation and they arrived at this and they were like, look, we have some quantity and then the quantity again, but it's final value and its initial value. Okay, so let's just name this quantity something. So when they came to this point, they said, I want to define K such that it is equal to 1 over 2 mv squared. So as a result of that definition, the net work is equal to the change in kinetic energy. Okay, just because we defined kinetic energy to be 1 over 2 mv squared. Because you can define it as mv squared and it all works out again, but the equation gets a little complicated. It scales up or scales down by a factor. Okay, this was just a side note. I hope the derivation makes sense. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.